Imagine a machine, basically the size of a two-story house.
Right, just this massive piece of industrial hardware.
Exactly. And inside this thing, it is violently crushing like 65 tons of solid rock into an explosive dust every single hour.
24 hours a day, 7 days a week.
Yeah. And the noise is deafening. The heat is intense. The physical forces at play are just staggering. But here is the crazy part. The people running this multi-million-dollar monster, which, by the way, is the foundation of our massive thermal power grid, they are essentially operating it completely blindfolded.
Which sounds insane, I mean, when you really think about it.
It does. And welcome to the deep dive. Our mission today is to explore these massive, hidden bottlenecks in heavy industry. Specifically, we're looking at how the silent mechanical degradation of coal pulverizers is costing thermal power plants millions of dollars.
Millions. And, we're also going to explore this radical new approach to industrial telemetry, a way to extract the physical mechanical truth from a machine without ever actually opening it up.
Right, which
Yeah.
is huge. Because the broader implications here, they extend way beyond just the energy sector.
Oh, absolutely. We are basically dissecting the anatomy of what the sources call scheduled ignorance.
Scheduled ignorance. I love that term.
It's a great term. It's this structural flaw built into almost every capital-intensive industry. You have the biggest, most expensive hardware in the world, degrading in total silence, and the operators are relying on a paper calendar rather than objective reality to manage it.
Right. So to break all this down for you today, we are working with a really fascinating stack of technical and strategic documents. First, we've got the highly technical specifications for the BHEL 1003 XRP bowl mill.
Which is quite a mouthful.
It is. But it's sourced directly from a performance guarantee test procedure from the NTPC Samhadri Stage 2 plant. We also have retailer and supply chain data from BHEL Hyderabad, which maps out the actual procurement cycle of the bowl mill spares.
Yeah, the actual replacement parts.
Exactly. And finally, tying the mechanical stuff to the conceptual, we have a series of strategic engineering essays on something called restorative engineering, motor current signature analysis, or MCSA, and this industrial philosophy of the quiet architect.
It's such a remarkable collection of sources because, it bridges the microscopic physics of grinding coal with this really high-level operational strategy.
Yeah.
You've got the raw thermodynamic requirements of a power plant sitting right next to this, asymmetric business playbook for disrupting original equipment manufacturers.
So you might be asking yourself, why should you care about the internal wear rates of a coal pulverizer?
Yeah.
Unless you are literally the plant manager at Samhadri Stage 2, why spend this hour looking at this?
Right. Fair question.
But we're framing this not just as a masterclass in heavy mechanical engineering. This is a blueprint for identifying hidden friction in literally whatever system you operate.
Yes.
Whether you are managing massive digital infrastructure, building a hardware startup, or, trying to optimize an opaque supply chain. This is about learning how to locate invisible degradation, capture control points, and bypass these entrenched monopolies that just profit from your lack of visibility.
Right. But, to understand why the machine fails, you first have to know how it's actually supposed to work.
Of course.
The mechanical reality of a thermal power plant is rooted really deeply in combustion chemistry. Ultimately, the whole point is just to boil water to turn a steam turbine.
Which is funny when you think about it. All this advanced tech,
Yeah.
You're basically just boiling water.
Exactly. It's a giant kettle. And coal remains this dominant energy source globally because of its base cost, the sheer availability of it, and the fact that it's super easy to transport a solid fuel.
Yeah.
But you can't just take massive chunks of raw, mined coal and throw them into a modern high-efficiency steam generator.
Right. Because if you try to burn a literal boulder of coal, the thermodynamics just completely work against you. It's all about surface area to volume ratios.
Yeah.
If you ignite a solid block of anything, it burns slowly from the outside in. So a massive amount of the thermal energy produced is wasted just trying to heat up the dense interior core of the rock, before it can even reach ignition temperature.
And in a power plant, that slow, localized burn is incredibly inefficient. They can't wait for that.
No. The plant needs an instantaneous, highly controlled release of energy.
Which is why the industry relies on pulverized coal.
Right.
By grinding the coal down to this microscopic powder, you drastically increase the surface area available to react with oxygen. To put it in perspective, if you take a 1 centimeter cube of coal, it has 6 square centimeters of surface area.
Okay, sure.
But if you crush that exact same cube into particles the size of a human hair, the total surface area increases by orders of magnitude. So when you inject that cloud of fine dust into the boiler mixed with preheated air, the combustion is essentially an immediate, continuous, controlled explosion.
And the sources make this really direct link between the pulverization process and the plant's ability to actually utilize low-grade coals.
Yes, that's crucial.
Because if you have a highly efficient pulverizer, you can buy cheaper, lower calorific value coal, grind it incredibly fine, and still extract enough thermal energy to hit your power output targets.
Right.
But if the pulverizer degrades, the boiler literally starves.
Exactly. The entire combustion process is held hostage by the mechanical grinding efficiency of the bowl mill. The bowl mill spares we're looking at today, these components procured from BHEL Hyderabad, they are the frontline mechanisms supporting this continuous energy production.
Right, they're the things actually doing the work.
Yeah, and they do this by mastering three very distinct physical principles of particle size reduction. We've got impact, attrition, and crushing.
Okay, impact, attrition, and crushing.
Now, people use those interchangeably in casual conversation all the time.
Oh, for sure. Crushing, smashing, whatever.
Right, but in mechanical engineering, they describe entirely different transferences of physical force.
Okay, let's isolate those three principles, starting with impact. So impact is kinetic. It's a sudden, high-velocity striking force.
It's like a hammer.
Exactly. If you swing a heavy sledgehammer against a brittle stone, that sudden transfer of immense kinetic energy creates a shock wave. It travels through the material and causes it to shatter along its internal fault lines.
Right.
And in specific types of high-speed pulverizers like hammer mills, you literally have heavy steel elements spinning at massive RPMs, violently striking the airborne coal particles, basically shattering them mid-air.
Right, so that's impact. But contrast that rapid shock wave with crushing. Crushing is the application of continuous heavy compressive pressure.
Okay.
It relies on overcoming the structural yield strength of the material through sheer physical force. So imagine placing a rock in a hydraulic press.
Oh, I've seen those videos online.
Yeah. The press doesn't strike the rock, right? It just slowly squeezes it.
Yeah, relentless pressure.
Exactly.
Wow.
So in vertical coal mills, crushing happens when these massive spring-loaded metal rollers press down against a rotating bed of coal. The coal gets trapped between the roller and the grinding bowl, and that downward force just crushes the rock into fragments.
Okay, which brings us to the third principle, which is attrition. So if impact is a sudden strike and crushing is a continuous squeeze, attrition is basically friction.
Exactly.
It's the abrasive rubbing and shearing forces acting between the particles themselves and between the particles and the metal surfaces.
Yeah.
If you take two rough stones and grind them together, you produce sand.
Right.
And inside the pulverizer, as the coal is trapped under those massive rollers, the particles are grinding against each other under immense pressure. It's this frictional tearing action that strips away the outer layers and reduces that fractured coal down to an ultrafine, microscopic dust.
And vertical coal mills, specifically the BHEL 1003 XRP bowl mill we're analyzing, they are engineered to utilize a highly specific ratio of these forces.
Okay, so they don't just use one.
No, not at all. While a hammer mill relies almost entirely on impact, this XOP vertical mill is built around a combination of crushing and attrition. The geometry at the bowl mill spares so. The massive grinding rolls pressing against the bull ring segments on the rotating bowl, it creates this optimal environment.
For crushing and friction.
Yes. Heavy compressive crushing, followed immediately by high friction attrition as the material is physically squeezed out from under the roll.
And the engineering documents, they also classify these pulverizers based on their operating speed, right?
Right.
Low speed, medium speed, and high speed.
Right.
And the speed of the mill directly dictates which of those physical forces is really doing the heavy lifting.
Exactly. So low-speed mills, like traditional tube or ball mills, they operate really slowly, maybe 15 to 30 RPM.
It's practically crawling.
It is. They use the cascading weight of thousands of steel balls tumbling inside a massive rotating cylinder to slowly crush and grind the coal. It's super reliable, but it's slow, and it consumes a massive physical footprint.
Right.
Then you have high-speed mills, which operate well over 1,000 RPM.
Wow.
Yeah, they act like industrial blenders. They rely purely on the violent impact of spinning blades.
So where does our BHEL XRP mill fit into that?
It falls right in the middle. It's a medium speed classification. It typically operates around, say, 40 to 70 RPM, depending on the specific model size.
Okay, so it's a compromise.
A critical engineering compromise. It provides enough centrifugal force to throw the raw coal outwards toward the grinding path on the bowl, but it moves slowly enough to allow those massive rollers to apply sustained compressive crushing force.
Okay.
It basically balances the power consumption of the electric motor with the required wear rates of the bowl mill spares, all while delivering the exact fineness required by the boiler.
And that term fineness, it's doing a lot of heavy lifting in these documents. The sources just repeatedly emphasize how crucial fine coal particles are for maintaining flame stability during combustion.
Oh, flame stability is everything.
Right. So if the bowl mill spares are doing their job, the grinding process supports incredible thermal plant efficiency. But how exactly does particle size dictate the stability of a massive fireball inside a boiler?
It's a great question. Flame stability is basically the holy grail of thermal operations. A stable flame means the combustion is continuous, it's anchored right at the burner nozzle, and most importantly, it's predictable.
Okay.
The heat transfer to the water-filled boiler tubes is steady, which keeps the steam pressure perfectly aligned with what the turbine is demanding. So when the coal is pulverized down to that required microscopic dust, it mixes intimately with the preheated combustion air.
So every particle gets oxygen.
Exactly. Every single carbon particle is surrounded by the precise amount of oxygen required for complete ignition.
So when that fuel-air mixture hits the ignition zone, it just combusts instantly and completely. There's no lag.
None at all. But if the pulverizer's grinding elements degrade, like if the rollers lose their pristine crushing geometry, the mill starts rejecting larger, coarser chunks of coal right into the boiler.
Uh-oh.
Yeah. And remember what we said about surface area.
Like, larger chunks have a lower surface area to volume ratio.
Exactly. They take longer to heat up, they take longer to ignite, and they take longer to burn completely.
Which just introduces massive operational chaos. You get delayed combustion, the flame becomes ragged, it pulses, it literally detaches from the burner.
It's dangerous.
Yeah, and in worst-case scenarios, an unstable flame can just blow out entirely, causing the boiler to trip, which shuts down the power generation and requires this massive, complex, expensive restart procedure.
And even if it doesn't blow out, those heavy, coarse chunks of coal might not finish burning before they literally fall out of the suspension. They just drop to the bottom ash hopper as unburned carbon.
Unburned carbon is literal capital being thrown into the ash pit.
Exactly.
The plant paid to mine the coal, transport it, handle it, and blow it into the boiler, only to fail to extract its thermal energy. That unburned carbon directly reduces the overall thermal efficiency of the entire multi-billion-dollar facility.
It's just waste.
Total waste. This is why the mechanical integrity of a few cast iron bowl mill spares dictates the economic viability of the entire grid. Let me use an analogy here to ground this for you.
Okay, let's hear it.
Think about dialing in the perfect shot of espresso,
Oh, nice.
right? If your coffee grinder's burrs are worn out or you set the grind too coarse, what happens? The hot water under pressure just channels right through the gaps between the large coffee chunks.
Right. It takes the path of least resistance.
Exactly. And you get a weak, sour, under-extracted shot because the water didn't have enough surface area to interact with. The energy of the water is wasted. But if you calibrate the grinder to produce a perfectly uniform fine powder, the water has to fight its way through that dense puck.
And you get that rich crema.
Exactly. The extraction is rich, stable, and maximizes the potential of the bean.
That parallel holds up perfectly. In the power plant, the hot combustion air is the water, the coal is the coffee bean, and the BHEL bowl mill is your industrial grinder. If the mill is producing coarse particles, your boiler is experiencing severe under-extraction. The heat isn't released efficiently, the flame is weak, and the plant bleeds operational capital.
So to achieve this perfect, consistent extraction at an industrial scale, we have to look inside the black box. The BHEL NTPC Simhadri Stage 2 Performance Guarantee Test Procedure, that document gives us the exact operational rulebook for a 1003 XRP bowl mill.
It dictates the physical reality that these machines just have to survive.
And a performance guarantee test is a really high-stakes engineering audit. Before NTPC, the massive Indian power utility, before they accept this equipment and pay out the contract to BHEL, the manufacturer has to prove the machine can hit mathematical targets under real-world stress.
Right. They can't just trust the brochure.
Exactly. And the technical specifications demand a base capacity of 65 tons per hour.
Now, processing 65 tons of solid rock every hour requires an environment that is almost hostile to machinery. But the contract doesn't just demand 65 tons blindly. It specifies that this capacity is guaranteed only under a very specific, quote, design coal condition.
Right, the baseline.
Yeah. The sources list a maximum of 14% total moisture and a hard grove grindability index, the HGI, of 55.
Okay, let's pause. Hard grove grindability index.
Right.
What does an HGI of 55 actually mean in the real world?
So the HGI is a vital standard in the industry. It quantifies the physical resistance of the coal.
Okay.
It's determined in a laboratory. They take a specifically sized sample of coal, place it in a miniature grinding machine, apply a very specific weight, turn it exactly 60 revolutions, and then they literally measure how much fine powder was produced.
Oh.
A lower HGI number means the coal is structurally denser, it's harder to grind. A higher number means it's softer.
Okay, so when BHEL guarantees 65 tons per hour and an HGI of 55, they are setting a baseline. If the plant decides to buy a cheaper, harder seam of coal with an HGI of, say, 45, the physical resistance inside the mill spikes.
Dramatically.
The rollers have to work harder, the crushing forces struggle to break the denser molecular bonds, and that 65-ton capacity might drop to 55 tons.
Exactly. This is why the test procedure includes these highly complex capacity correction curves.
Math formulas to adjust the expectations.
Right. Mathematical formulas to adjust the performance expectations if the actual coal burned during the test deviates from the design baseline. But capacity is only half the equation here.
What's the other half?
Fineness. The test procedure imposes astonishingly strict fineness requirements. The guarantee states that 70% of the pulverized coal must pass through a 200 mesh sieve.
Okay, a 200 mesh sieve means there are 200 microscopic openings per linear inch.
Yeah.
To pass through that, a particle has to be smaller than 74 microns. We are talking about particles finer than standard baking flour.
It's basically dust.
And simultaneously, the document demands that 99% of the coal must pass through a 50-mesh sieve, meaning there is zero tolerance for larger rogue chunks escaping into the boiler.
And to force 65 tons of rock through a 74-micron threshold every single hour, the mill must maintain an incredibly aggressive internal aerodynamic environment.
Right.
The test specifies the mill outlet temperature must be maintained above 78 degrees Celsius.
Why so hot?
Because they use the primary combustion air to simultaneously dry the coal as it grinds. Remember that 14% moisture we talked about? If that moisture isn't evaporated instantly, the coal turns into this dense paste. It clogs the internal classifiers and basically blinds the grinding path.
Oh, wow. And the aerodynamic forces, those are measured by the differential pressure, right, the DP. The guarantee states the DP across the mill cannot exceed 300 millimilli WC, which stands for millimeters of water column. Let's translate 300 millimilli WC into physical reality for a second.
Okay.
If you dive about a foot underwater with a snorkel, the pressure of the water trying to collapse your lungs is roughly 300 millimilli WC.
It doesn't sound like a lot when you say it like that.
It doesn't. But imagine scaling that up to a massive steel chamber. You have giant fans blasting hot air trying to lift 65 tons of microscopic rock dust vertically out of the mill, while that exact equivalent pressure is fighting back as air resistance.
It's a delicate aerodynamic balancing act. The differential pressure measures the resistance the air faces as it moves from the bottom of the mill through the grinding zone, past the classifiers, and out the exhaust pipes.
Okay.
If the grinding rolls lose their efficiency, or if the internal rotating classifier fails to separate the fine dust from the coarse rocks, the internal volume of the mill becomes choked with circulating coal. The air just cannot pass through easily, and the differential pressure spikes beyond that 300 millimilli WC limit.
And when the pressure spikes, the dust isn't escaping to the boiler. It's just settling back onto the grinding bowl, cushioning the impact of the rollers, and further ruining the crushing efficiency.
Exactly. It's a catastrophic feedback loop.
So to prevent this, everything relies on the mechanical integrity of the key wear parts. The exact bowl mill spares, documented in the BHEL Hyderabad supply chain data. The primary components being those massive grinding rolls and the bowl ring segments that line the rotating bowl.
Right. And the architecture of the 1003 XRP mill places these parts under immense continuous stress. You have a massive cast iron bowl rotating at the base. Lining that bowl are the bowl ring segments, which basically form a hardened grinding track.
Okay.
Suspended above this track are 3 massive independent grinding rolls. These rolls are mounted on pivot shafts and forced downward by incredibly heavy pre-tensioned mechanical springs.
So as the bowl rotates, Centrifugal force pushes the raw coal outward onto the bullring track. The coal is literally dragged under the stationary spring-loaded grinding rolls.
Yep.
The springs force the roll down, generating the compressive crushing force, while the difference in speed between the rotating bowl and the rolling wheel generates the frictional attrition.
And millions of tons of abrasive rock are dragged through that narrow high-pressure gap over a cycle of, say, 9,000 to 12,000 hours of continuous operation. That cast iron physically degrades.
It just wears away.
Yeah. The pristine engineered geometry of the roller faces gets chewed away. They become pitted, grooved, and flattened. The gap between the roll and the bowl widens. The crushing force becomes less concentrated, and the attrition becomes less effective.
Which brings us to a section of the NTPC technical logs that is truly staggering from an operational standpoint. I mean, we had these massive vital components slowly destroying themselves inside a sealed, violently loud, dark machine.
Right.
And the plant operators need to know exactly how much geometry has been lost so they can optimize the spring tension or prepare for a replacement. The sources detail the traditional wear life assessment methodology. I mean, it highlights a massive technological blind spot.
It really does. Historically, and in many plants currently, the only way to assess the physical degradation of the grinding rolls is a manual physical measurement.
Which involves shutting everything down.
Oh, completely. The procedure requires the plant to take the mill out of service. They shut off the coal feeder, purge the mill of explosive dust, lock out the massive electrical motors, and then they have to wait for the multi-ton steel casing to cool down from 80 degrees Celsius.
Just sitting there waiting.
Yeah. Then operators physically open these massive access doors, enter the confined space of the mill housing, and manually apply a specialized wear measurement gauge against the surface of the grinding rolls.
And the document specifies they have to take these readings at 3 specific positions, right?
Right, 120 degrees apart around the circumference of each roll.
Measuring the gap between the worn surface and a reference template mounted on the lower journal housing. And they do this manual shutdown and measurement process every 1,000 hours of operation.
Every 1,000 hours.
Which is just, from an operational standpoint, isn't that just insanely inefficient? You shut down a massive power plant mill just to stick a gauge on a piece of metal. It sounds like you're operating completely blind for 999 hours at a time.
I agree strongly with you on that. From an engineering legacy perspective, sure, this was the only way to ensure safety. In the 1980s and 90s, you couldn't run complex simulations on the fly.
Right.
If you didn't physically verify the wear, a roller could degrade to the point of mechanical failure, which could spark a massive dust explosion inside the mill housing.
Obviously bad.
Very bad. The risk was too high, so they accepted the operational penalty of shutting down the mill to look at it.
The historical context makes sense, but looking at it through a modern industrial lens, it is an operational nightmare. You're operating completely blind for 999 hours, you're running a machine processing millions of dollars of fuel, and your only telemetry on the most critical wear parts is a physical ruler applied once every month and a half.
It's why
The plant absorbs the massive opportunity costs of the downtime, the labor costs of the confined space entry, and the thermal stress on the equipment from cooling down and reheating.
And during those 999 hours of darkness, the plant has no idea if the wear rate is accelerating due to a bad batch of highly abrasive coal. They only realize something is wrong when the external symptoms hit the control room, when the differential pressure spikes over 300 mmWC, or when the boiler starts dropping temperature because it's starving for fine coal.
Lagging indicator.
Exactly. By the time those lagging indicators appear, the plant is already bleeding operational capital.
And this exact 1,000-hour blind spot is what the strategic engineering essays in our sources call scheduled ignorance.
Yes, scheduled ignorance.
And this is where the narrative shifts from mechanical engineering into a high-stakes business strategy. The essays introduce a framework called the founder-grade market lens.
I love this concept.
Yeah. This lens asks you to look at a complex system, find the hidden friction, and identify exactly who profits from the opacity. In the world of coal pulverizers, who benefits from scheduled ignorance?
The original equipment manufacturers, the OEMs.
The OEMs.
They build the mills, they supply the proprietary replacement parts, and they hold the ultimate control point. Heavy industry operates on a model where capital expenditure, the CapEx, is heavily protected. A power utility will spend 2 years negotiating the initial purchase price of a fleet of bull mills just to shave off a few percentage points of the cost.
Right. They fight tooth and nail up front, but then they immediately start bleeding operational expenditure, the OpEx.
Because they can't see what's happening?
Because the physical wear of the internal components is invisible during operation, the plant operators cannot confidently predict exactly when a grinding roll will fail.
Yeah.
They cannot risk running the mill to the absolute limit of the part's viable life. To mitigate the risk of an unscheduled catastrophic failure, they lock themselves into rigid, calendar-based maintenance contracts dictated by the OEM.
The OEM sets the schedule. They state that the bull mill spares must be replaced every 10,000 hours of operation, regardless of the objective mechanical condition of the metal.
Just on a schedule.
Exactly. The plant managers comply because they lack the telemetry to prove otherwise. They pull out perfectly functional cast iron rolls that might have 2,000 hours of highly efficient crushing life left in them, simply because the calendar says it's time.
It's a brilliant, entirely legal, deeply entrenched monopoly based entirely on the absence of data. The OEM sells the massive machine at a competitive margin, but they secure a multi-decade revenue stream by selling expensive, heavy metal replacement parts at an artificially inflated frequency.
Right. The bottleneck is visibility.
The plant absorbs the financial friction because they cannot see the geometric wear while the machine is spinning.
Breaking this control point requires what the essays call an asymmetric advantage. You cannot beat the OEM by building a better wear measurement gauge, and you cannot beat them by visually inspecting the mill more often because the downtime cost negates the savings.
So what do you do?
The strategic essays propose a radical alternative through restorative engineering. You bypass the physical casing of the machine entirely and extract the mechanical truth from its electrical shadow.
Okay, this introduces the core technological concept, motor current signature analysis, or MCSA. The goal is to perfectly map the physical degradation of massive steel components mathematically in real time without ever opening an inspection door.
It's basically magic.
Walk us through the physical laws that make this possible. How does an electrical wire tell you the shape of a piece of cast iron?
The foundation of MCSA rests on the relationship between mechanical load and electrical current in an induction motor. The massive electric motor driving the BHEL XRP mill is pulling power from the grid to turn the planetary gearbox, which rotates the heavy grinding bowl.
Right.
The current it draws is not a perfectly flat, smooth line. It's a complex waveform filled with microscopic fluctuations, harmonics, and noise.
It has a signature.
Exactly. When the internal geometry of the grinding rolls degrades, the physics of the crushing process changes. The mill becomes less efficient, the coal doesn't break as easily, the rotating bowl faces more physical resistance, and the machine has to literally push harder to maintain its RPM against the 65 tons of abrasive rock.
And that increased physical resistance demands more torque from the motor.
Yes, and to generate more torque, the motor immediately draws more electrical current. The mechanical strain translates instantly into an electrical anomaly.
The variations in the mechanical load cause microscopic modulations in the amplitude and frequency of the stator current.
Right.
By utilizing incredibly sensitive electrical sensors, high-frequency clamp-on ammeters, engineers can capture this raw electrical waveform. You are no longer trying to look at the metal, you are looking at the direct energetic cost of moving that metal.
But the reality of a power plant is noisy. The electrical grid fluctuates. The incoming coal might suddenly drop from an HGI of 55 to an HGI of 45, making it harder to grind. The motor itself has inherent vibrations. How do you isolate the tiny, specific signal of cast iron roller wear from the massive, chaotic noise of the industrial environment?
You can't do it with electrical data alone, can you?
No, you can't. The genius of the approach detailed in the sources is the fusion of datasets. You cross-reference the high-frequency MCSA data with the existing lagging indicators from the plant's central control system, the SCADA data. Specifically, you look at the differential pressure metrics we discussed earlier.
The air resistance, the 300 millimillia WC limit.
Correct. If the electrical signature suddenly shows increased mechanical strain, that could just be a hard batch of coal.
Right, a false positive.
Exactly. But if the MCSA data shows a slow, progressive increase in a specific frequency band over 3 months, and simultaneously the SCADA data shows a slow, proportional creep in the differential pressure, you have a correlation. The engineering models use complex math, like fast Fourier transforms, to isolate the specific electrical frequencies that match the rotational speed of the grinding rolls.
You filter out the noise of the grid, you filter out the noise of the fan, and you isolate the exact electrical frequency of the roller hitting the bowl.
Exactly.
Over time, you train an inference model to recognize the exact electrical pattern of a pristine roller versus a worn roller. You are essentially using the electricity as a high-definition millimeter wave radar to mathematically map the internal geometry of the steel.
The analogy often used in diagnostics is an electrocardiogram, an ECG.
Oh, that makes sense. A cardiologist doesn't need to perform open heart surgery to determine the physical geometry of your heart valves or to see if a specific ventricle is struggling.
Right, they don't cut you open.
They place non-invasive electrodes on your skin, capture the electrical impulses generated by the heart muscles, and read the signature. The electrical current reveals the precise physical mechanics of the hidden organ.
MCSA is an ECG for heavy machinery. It is entirely non-invasive. You don't drill into the casing, you don't install fragile optical sensors inside an 80-degree-Celsius dust storm. You sit securely in the electrical control room and you read the shadow.
It's brilliant.
And the essays don't just leave this as a theoretical exercise. They provide a precise, aggressive business playbook for deploying this technology to shatter the OEM's maintenance monopoly. They call it the 48-hour asymmetric bet.
The 48-hour bet is a masterclass in proving value without asking for permission or massive capital. In the industrial software space, startups often try to sell multi-million-dollar plant-wide pilot programs that take years to integrate.
And nobody wants that.
No. This strategy flips that entirely. You approach the plant manager and ask for a localized zero downtime test. You ask to install a single high-frequency clamp-on ammeter on the power feed of one active coal mill.
And a clamp-on ammeter simply wraps around the exterior insulation of the power cable. You don't cut the wire, you don't interrupt the current, and you don't shut down the mill. It takes 5 minutes.
You log the high-frequency MCSA data for exactly 48 hours. Simultaneously, you request the plant's existing differential pressure logs for that exact same window. You feed this data into your inference model, identify the structural anomalies in the electrical current, and correlate them against the plant's historical maintenance logs. You look at the last time they performed that archaic 1,000-hour manual gauge measurement.
And then you walk back into the plant manager's office and show them the math. You show them that the electrical data perfectly mirrors the physical wear pattern they manually measured a month ago, and you show them the microscopic progression of wear that has occurred since they last closed the doors.
You prove decisively that the machine's electrical shadow is telling the truth.
In 48 hours, you have completely decoupled the wear rate from the visual inspection. The essay states explicitly, quote, "Once you map the wear curve, you control the maintenance schedule. The OEM becomes a commoditized parts supplier." The plant manager is no longer operating on scheduled ignorance. They have the telemetry to say, the OEM manual says replace the rollers today, but my MCSA data shows the geometric crushing efficiency is still at 92%. We are running them for another 2,500 hours. You return the operational control to the utility based on objective mathematical reality.
Scaling this concept from a single 48-hour test to a plant-wide telemetry system introduces the hardware component of our sources. The text details a specific industrial project proposal, playfully codenamed Nano Banana 2, Mill Telemetry Edition.
I love that name.
It's great. But while the name is lighthearted, the engineering philosophy behind it is profound. How do you actually deploy MCSA across dozens of massive mills without overwhelming the plant's IT infrastructure?
Well, the traditional Silicon Valley approach would be to capture massive amounts of raw, high-frequency electrical data and stream it all to a centralized cloud server for processing.
Dump into the cloud.
Right. But in heavy industry, that is often a fatal flaw. Industrial sites have notoriously poor internet bandwidth, and plant managers are rightfully paranoid about cybersecurity and streaming operational data offsite. The Nano Banana 2 solves this by utilizing edge computing.
It's a localized compute device.
Yeah.
The proposal describes a packaged microprocessor fully integrated with current transducers and an interface for the plant's existing pressure sensors. It sits physically right next to the motor control cabinet.
Yes.
The critical difference is that the data processing happens locally on the edge of the network rather than in the cloud.
The Nano Banana 2 is running the trained inference model locally on its own silicon. It ingests the massive, chaotic stream of raw electrical noise, applies the fast Fourier transforms, filters out the grid anomalies, and isolates the mechanical wear frequencies in real time.
It doesn't send gigabytes of raw data to the control room.
No, it translates the electricity into a clean, highly compressed 2D geometric wear map of the internal parts and sends only that insight forward.
It absorbs chaos and outputs clarity. And the proposed monetization strategy for this device perfectly aligns with the goal of eliminating the financial friction. You don't sell the Nano Banana 2 for a massive upfront hardware cost.
Oh, no.
The proposal suggests offering independent power producers a 30-day free shadow deployment. You clamp the devices onto their mills at your own expense and let them quietly watch the electricity for a month.
And after 30 days, you present the plant with an objective dashboard showing the exact remaining lifespan of their bowl mill spares. You reveal the life left in the parts that the OEM calendar is telling them to throw away.
Right.
The revenue model is entirely performance-based. You charge a software as a service fee equivalent to 10% of their deferred OEM replacement costs.
If your edge device proves they can safely defer a $500,000 grinding roll replacement by 6 months, you take a $50,000 cut of the capital you just saved them. You are directly monetizing the elimination of scheduled ignorance. It's a frictionless sale because the plant pays you out of the budget they had already resigned themselves to giving to the OEM.
This business model is the practical application of a much deeper industrial philosophy discussed in the sources. The ethos of the quiet architect and the concept of restorative engineering.
Yeah.
The author of the strategic essays connects the telemetry of a coal pulverizer to seemingly unrelated fields, specifically robotics and bioprinting.
This is where the engineering manual ascends into a profound observation about technology's role in society. The text proposes a fundamental thesis, quote, "Real technology doesn't replace people, it restores them. It restores capability. It restores dignity."
The author details their prior experience deploying robotic systems into high-risk manufacturing environments. They observed factory workers handling live explosives, literal grenades, on an assembly line.
Which is terrifying.
Yes. The workers were operating under immense, continuous psychological and physical friction. The engineering solution was to integrate a TechMan cobot, a collaborative robotic arm, to handle the explosive payload. The primary metric of success for that deployment wasn't a 5% increase in throughput or the automation of a job for cost savings.
The metric was safety. The technology removed the worker from the blast radius. It restored a sense of security to a highly volatile environment.
And the text then connects this to the development of bioprinters, engineering biological tissue and organs before a patient's time runs out. Whether you are building a robotic arm to handle explosives, a bioprinter to replace a failing liver, or a nano-banana two-edge device to monitor a degrading coal mill, the underlying logic of the quiet architect remains identical.
You are locating the hidden friction in a complex system. In the munitions factory, the friction was the catastrophic physical risk of explosion. In the hospital, the friction is the invisible, relentless biological decay of the human organ. In the thermal power plant, the friction is the unseen mechanical degradation of the cast iron grinding rolls.
Exactly.
The quiet architect uses applied technology to measure the invisible, mitigate the risk, and restore the operational capability of the system.
It is an explicit rejection of performative, hype-driven engineering. The goal isn't to build flashy, disruptive apps that monopolize attention. The goal is to build grounded, consequential tools that optimize heavy physical realities without demanding the spotlight. You extend the life of the worker, you extend the life of the patient, and you extend the life of the multi-million-dollar infrastructure.
This philosophy of quiet, functional truth is perfectly mirrored in the physical design aesthetic dictated for the Nano Banana 2 module. The visual prompts in the sources explicitly demand a design language based on the Dieter Rams Braun aesthetic from the mid-20th century.
Rams believed in less but better.
Right. Design should be unobtrusive, honest, and purely functional.
The visual contrast described in the prompt is striking. It places the pristine, bead-blasted aluminum casing of the Edge compute module directly against the heavy, brutalist, micro-abrasive reality of the cast iron pulverizer.
Just a stark difference.
The coal mill is chaos, vibration, grease, heat, and violent crushing forces. The Nano Banana 2 is order. It's a minimalist, perfectly machined rectangle featuring a single recessed status indicator light in a muted cadmium orange.
There are no glowing neon cyberpunk screens, no complex arrays of flashing lights. It absorbs light rather than reflecting it. It does not try to intimidate the plant operators with technological complexity. It looks like a reliable, highly calibrated instrument.
Exactly.
The visual design is a metaphor for its operational purpose, taking the raw, violent physical degradation happening in the dark and translating it into clean, quiet digital legibility.
The honesty of the Dieter Rams aesthetic aligns perfectly with the objective truth of the MCSA data. The materials read accurately, the data strips away the noise, the fear of the unknown, and the self-serving narrative of the OEM maintenance calendar, leaving the operators with nothing but the mechanical reality of their machine.
This entire deep dive forces a profound reevaluation of how we manage complex environments. We have spent the last hour dissecting the physics of crushing coal, the absurdity of shutting down a massive machine just to hit it with a metal ruler, and the elegant mathematics of using an electrical shadow to map physical degradation. But the core lesson here transcends mechanical engineering. I want you to apply the founder-grade market lens to your own operational reality.
It's a powerful tool.
Where are the sealed environments in your business or even your personal life that are quietly bleeding resources simply because you are relying on a predetermined calendar instead of actual telemetry?
It's the trap of scheduled ignorance. In corporate structures, are you replacing software, restructuring teams, or abandoning strategies just because a quarter ended or because an external consultant's timeline said it was necessary? Or do you have the internal telemetry to understand the actual functional wear and tear on those systems?
Are you locked into an intellectual or operational maintenance contract with an entrenched monopoly that profits from your lack of visibility?
Right.
Whether it is supply chain logistics, employee performance metrics, or digital infrastructure, friction almost always develops in the dark.
And the journey today illustrates that the tools to illuminate that darkness often exist just outside the traditional framework.
Right.
The power plant operators couldn't see the metal, so they learned to read the electricity. They found an asymmetric proxy for truth.
You have to find the electrical shadow of your own hidden bottlenecks. You must locate the friction, find a way to measure the invisible degradation, and ultimately reclaim control of the data layer from whoever is currently profiting off your blindness.
The scale of the system doesn't grant it immunity from decay. The massive thermal power plant projects an aura of absolute permanence. But beneath the steel casing, it is constantly fighting a losing battle against the physics of attrition.
We leave you with a final thought to mull over. We have focused extensively on how heavy hardware fails in silence and how localized edge telemetry can give that hardware voice. But consider the human and organizational systems you rely on daily. Your corporate management hierarchies, your local community infrastructure, the massive logistical networks that deliver your goods.
Those are systems too.
These are also complex, high-pressure, often sealed environments. They too experience continuous internal friction. They often degrade in total silence, long before the breakdown becomes visible to the end user. If you could attach an organizational clamp-on ammeter to measure the invisible structural friction within your own company or community, what silent degradation would you discover before the system reaches its breaking point? We started this deep dive talking about the comfort of certainty, the illusion that massive systems just work simply because they are large. But the truth is, nothing is permanent without maintenance. The only question left is whether you're going to continue maintaining it blindly or if you're finally ready to read the shadow.